Assalamualaikum and good day. My name is Muhammad Asran bin Lataga, together with my partner Fidaa bin Ahmad Fahmi. So today we will present our IoT project titled Smart Intruder System. So this project is developed for the Internet of Things IoT course and focuses on securing a real pilot aquaponic farm known as the Oasis. Before we go further, let me introduce you to the environment where our system is deployed. So this is the Oasis. The Oasis is a pilot scale aquaponic greenhouse, approximately 5 to 6 square meters, operating in an open environment. So this system integrates fish rearing, plant cultivations, and water recirculations. However, during night operations, the greenhouse is exposed with limited visibility and open access. These make it vulnerable to unauthorized entry, physical disturbance, and tampering, especially when no operator is present. From our assessment, we identified four main vulnerabilities. First, there is a blind spot during nights and weekends with no operator is present. Second, physical disturbance can damage sensitive crops and aquaponic infrastructure. Third, the open access nature increases the risk of unauthorized human or animal intrusion. And finally, there is an information gap where operators only realize an intrusion after the event has already occurred. So this leads us to a clear design imperative, automated detection, and bridge the communication gap instantly. So based on the identified risk just now, we define the four core objectives. First, detect using multimodal sensing with motion and vibration sensors. Second, trigger by activating immediate local audio and visual alerts. Third, capture by securing visual evidence automatically using a camera module. And fourth, notify by sending real-time alerts with images to the user via Telegram. So these four pillars guide the entire system design.
Alright, for this slide shows the high level architecture of our systems. So the node MCU acts as the primary controller. It continuously monitors the PIR motion sensor and vibration sensor. When an intrusion is detected, the node MCU triggers local alerts and send a wireless HTTP request to ESP32 CAM, which act as a secondary processing unit. So the ESP32 cam then captures an image and sends it to the user through Telegram bot. Okay, now let's us summarize the main hardware components our IoT project. So the Node MCU ESP is selected for its reliable Wi-Fi capability and sensor handling. So the ESP32 cam is dedicated to image capture to avoid overloading the main controller. Then the PIR motion sensor detects humans' presence inside the greenhouse, while the vibration sensor detects physical tampering. So feedback is provided using LEDs and buzzers, forming a simple but effective local interface.
This flowchart explains the sensing logic implemented on the Node MCU. The vibration sensor is sampled at high speed to detect short spikes caused by tampering. If vibration exceeds the threshold, the system immediately triggers an alarm. For motion detection, we apply double check logic to reduce false positives. So only sustained motion results in an intrusion trigger. When no intrusion is detected, the system remains in safe state indicated by the green LED.
Okay, so the next is the handshake device to device communication because of use local Wi-Fi network. So we need to do handshake actually. So for communication between the two devices is done wirelessly. The Node MCU acts as a Wi-Fi client and sends an HTTP GET request to the ESP32 CAM's local IP address, and then the request includes a parameter indicating the cause of the alarm, such as motion or vibration. Then the ESP32 CAM passes this information and embeds into the Telegram notification. Once triggered, the cam handles all visual processing. It captures a high resolution image and balances image quality and compression and securely send the photo to the Telegram API bot. And then this ensures the visual evidence, is delivered almost immediately after intrusion detection.
So this slide shows you the primary user interface. So the Telegram alert includes a clear warning header, the cause of the alarm, a timestamp synchronized using NTP, and captured image as visual evidence. So this allows the user to assess the situation remotely in real time. In addition to Telegram, we implemented a lightweight web dashboard hosted on the Node MCU. So this interface displays the current system status and the last triggered sensor. It refreshes automatically and is mainly used for local monitoring, debugging, and demonstration purposes. At this point, we will show you a short 1 minute demonstration of the prototype in operation, including the intrusion detection and also Telegram alert delivery. Alright, so this is the prototype for our IoT smart intruder system. So we can imagine this as the farm of the greenhouse. This is the top of it, and then over there is the entrance. Okay, so when nothing happens, the LED will turn green like this. Alright, and then yes, when they detect a motion or detect a vibration, it will turn red. So that's the first one, which is the vibration sensor. So when it detect any vibration, it will trigger, right, and it will send a photo to the Telegram. So that's the first one. The second sensor is the motion sensor. So when it detect any motion, right, over here, it will turn red, and the camera will also capture the picture. So this is how it looks like. All right, so the camera will take picture at the entrance of the farm, and it will tell us which alarm is actually detected, either motion or vibration, and also the date and the time.
In conclusion, we successfully developed a functional and reliable IoT-based intruder detection system. The system integrates motion and vibration sensing with a real-time cloud and visual evidence. So, for future improvements, we see strongly potential in solar-powered autonomy, AI-based human and animal detection, and mesh networking for larger agricultural deployments. So this demonstrates that the system is not only practical but also scalable.
So that's pretty much everything. This project was developed by me, Muhammad Asran bin Lataga, and my partner Fidaa bin Ahmad Fahmi under the supervision of technologist Dr. Chin Kim On from the Faculty of Computing and Informatics, University Malaysia Sabah. Thank you for your attention.